Warm welcome to my dear friends. A very good morning, good afternoon, good evening to all of you, and welcome to this data analysis and decision making 1 under the NPTEL MOOC series. And this is with the total course duration, as you know, which I repeat at beginning of each class. This is for a 30 hours course, 12 weeks, and each week we have 5 lectures, and each lecture is of half an hour, and we are on the 22nd lecture, and I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, if you remember the last slide which we were discussing before we left, I will repeat that again when I am going to come. We have just started the concepts of multiple linear regression, and later on we will discuss something to do with the forecasting methods very briefly, and then go into other models and multivariate statistical methods. So, in multiple linear regression, what we want to do is that, with repetition I am saying, because I have already said that, but I did mention in the last class 21st lecture, the last slide, I would be coming back to this discussions time and again. So, in multiple linear regression, what the idea is basically you want to regress, that means go back, use the information about the information which is given by the independent variables. Consider there are k number of independent variables. In many of the books it is given as either small k or small p, and using this k or small p number of independent variables which are denoted from by x1 to xk or x1 to xp, you want to basically predict, forecast the yth variable which is the dependent one. And as you are doing it, there would be many different type of assumptions which we need to understand, such that it will be able to give you the maximum set of information for the prediction of y using xs. Now, multiple linear regression, or generally technically we should basically start with the simple linear regression. In simple linear regression, there is only one x, and given one x you have basically y to predict. So, where all the information which you have about x is subsumed such that x is able to predict y to the maximum possible value. Now, it does not mean that when you are using one x or multiple x's, you are able to predict y always with 100% accuracy. There would be an error. So, that error or the white noise would have some properties, and I did mention some of the simple properties when we are basically discussing what are the assumptions based on which multiple linear regression works. I will come to that again, but let us first start with simple linear regression and come back to multiple linear regression in all its details. So, under this method, the most important assumption is that the dependent variables which we denote by okay, I am sorry, then so we should have been basically x as bold in order to denote is a vector, but or matrix, but for the time being we will consider it is a simple linear regression. So, the important assumption is that the dependent variable which we denote by y, capital Y, is due to the effect of only one independent variable. In that case, obviously x is would be denoted not with a bold, and the nomenclature would change accordingly. I will come to that later on. So, you will basically have one x, and the x would basically have the values, and we will use those to basically predict the future values of y, and obviously there would be error, and we will try to tackle how the errors are handled and what are the properties. So, generally for the simple linear regression, again what we were discussing about the multilinear regression, I am going to come to that later on, please bear with me. For the simple linear regression, yi is given by alpha, and there is no suffix for alpha, plus beta, there is no suffix for beta, xi plus epsilon I. So, these i's basically means the reading number. So, if you have 10 readings, I would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, here are what the actual variables are. Y with the suffix are the set of dependent variables starting from 1 to n, considering there are n number of readings. Consider if it is time period, so it will be for January, February, March, April, May, June, so on and so forth. If it is basically for week, it would be first week, second week, third week and all the values. Now, alpha is basically the constant value. Technically, constant value would basically means that even if the x's values are 0, y does have a value which is alpha. And if you compare this equation with y is equal to m x plus c, you will find out some similarity there. Beta is basically the regression coefficients, and we will see later on it gives you the rate of change of the value of y with 1 unit change in x. So, consider that is the regression coefficients, and later on when there are the multiple linear regression, we will consider that they are the regression coefficients, that the partial regression coefficients. Why I am using the word partial, you will also understand that. And if you all of us know that the concept of partial differentiation, what they actually do is that we keep all other variables fixed and basically find out the rate of change of the function with respect to only one variable. So, partial differentiation is used for that case, and we will use the partial regression coefficients for in that context only. I will come to that when we do the multiple linear regression. So, you have betas, then you have basically multiplied by the xi's, xi's x as I mentioned just before this slide. These are the independent variables and the number of readings are 1 to n, and epsilon are the errors. So, the errors also are numbers 1 to n. Now, you may be thinking that what do we do with this equation? This basically we are trying to utilize the x values for 1 to n reading, y values from 1 to n reading, and trying to find out the values of alpha and beta, which are actually the population from the population which you are picking up, and trying to find an estimate of those population parameters such that when we predict for the nth plus 1 reading for y, considering that n number of readings are there, and for the nth plus 1 reading we do not have y, but we do have x, that means x suffix n plus 1 reading is there. We will use those values of x suffix n plus 1 in order to basically predict the nth plus 1 reading for y. And once the actual value of y is obtained, we will try to basically find out that what is the error, which is the difference between y actual value for the nth plus 1 reading and y predicted for the nth plus 1 reading. So, what I am saying that all are in words, and when I basically write those equations you will understand. Now, obviously, there would be some assumptions. So, what are the assumptions? The first assumption is the covariance or the relationship or the interrelationship existing between the errors and the dependent variable independent variables is 0 for all the readings y 1 to n. That means, the errors do not affect the independent variable x, and that will also be carried forward when you have more than one x, that means p x's or k x's. The second one is that the errors would have a distribution. Technically, we consider the distribution of errors is normal with 0 mean and 1 standard deviation in the simplest case. So, the second bullet point, when expected value epsilon 1 I is 0, it actually means that. The third one is basically the errors do not affect each other, hence the covariance existing between the errors from time period 1 to time period 2, time period 2 to time period 3 are all independent, hence this is 0, which means that we do not have the concept of heteroscedasticity in the problem, such that the errors by themselves are not changing. They are changing, but they are not changing in the sense that the distributions are not changing in their parameter values. The fourth information is that the variance has a value of the errors has a value of sigma square suffix epsilon. I did mention that in the simplest case we take the variance as 1, but in general sense we will take the variance of the errors to be some fixed value sigma square. And we consider the distribution of x to be normally distributed with the mean value of mu suffix x and variance of sigma square suffix x. And as x's are normally distributed, as epsilon are normally distributed, as x's are independent to each other with respect to epsilon, and obviously alpha being a constant value, and as per the properties of normal distribution, y would also have a normal distribution with a certain mean and a certain standard deviation. We are going to come to that. Now, let us find out the expected value of y and similarly the variance of y. So, the first part is for the expected value. So, when, as if you remember that I mentioned that when during the discussion, the equation y is equal to alpha plus beta x I plus epsilon, this is something like y is equal to m x plus c. Now, this you will find out comes out to be right when we solve the equation. So, what we are doing that I am going to come to that. So, let us take these, y has also a normal distribution with a certain mean and a certain standard deviation, alpha is a constant, x is basically also a normal distribution with a certain mean and certain standard deviation, epsilon is also an error with a normal distribution with a 0 mean and sigma square the variance. So, let us find out the expected value. So, if I find out the expected value of y, so that is this technically for the population. So, expected value of epsilon alpha is fixed is alpha, this is, so this becomes beta into epsilon x plus 0, because the expected value, let me write it, it is better, wait. This is the error and this becomes basically equal to 0. So, if you see it, the expected value of y here, the expected value of y is equal to alpha plus beta into expected value of x, which is mu x plus 0, because this is 0. So, this equation is obtained from here. Now, we need to find out the variance of y, and I will draw also in order to make you understand. So, once I finish, I will erase on this slide only and draw it. So, let us go to the variance. So, the variance of y, consider this is equal to sigma square suffix y. Now, we need to find out the variance for 3 terms, which is the first one, the second one and third one, and the covariance existing between the first and the second, second and the third, and the first and the third. Now, let us go one by one. The variance of alpha, which is a fixed quantity, is 0. Variance of beta into x I would be beta square into variance of x, because the variance of x is given. The third term is epsilon y, epsilon. So, hence the variance of epsilon as per the assumptions is sigma square suffix epsilon. So, all these first three parts are done. Now, let us come to the covariance factors. Now, the covariance, if I consider for alpha, which is the constant value with respect to any random variable, would be 0, which means the covariance existing between the first term and the second term is 0. Covariance existing between the first term and the third term is 0. Now, let us consider the covariance existing between the second term and the third term. Now, covariance between the second term and third term would be 0, because we have intrinsically assumed before we started solving this problem that the errors do not affect x and vice versa. Hence, the covariance existing between x and epsilon is 0. So, what are the terms left? There is no covariance term. First term variance of alpha is gone, only the variance of the second term and the third term is there. Second term variance is beta square sigma square x, and the variance of the third term is given by sigma square epsilon. So, if you check the formula, so this is the equation we found out and this matches here. So, both the expected value and the variance for the y, which is the dependent variable, have been proved. Now, you would be saying that I have promised that I will try to draw and illustrate that, I will do that. So, let me erase whatever I have basically done. Oh yeah, I'll missed one thing, I'll come back to that later. Just 1 minute before I draw. So, if you remember this equation, and I had said y is equal to mx plus c. So, this is the equation which you have done when you were kids. So, this is the equation y is equal to mx plus c. This basically matches this. So, this is basically c, this is beta is m and x is the expected value. Now, let us draw it. So, I will basically use a color. So, these are the axes and you have the values of x with y as this. So, now I draw a line, consider this is the line. So, if I consider the first point, point 1, 2, 3, 4, so on and so forth. So, the first point, and obviously this is basically, so this equation would have an error. So, actual value is of y is here, predicted value of y is the straight line. So, obviously this is an error. So, this is basically epsilon 1, which is the error for reading 1. Second equation, actual y is here, predicted value is y is here. So, this is epsilon 2. Similarly, this straight line is epsilon 3, epsilon 4, epsilon 5, 6, 7, 8. Now, if you consider the errors as such, so these are the errors. So, technically if I draw the errors, so there is some positive error. So, this is the first one. So, I will mark them as I will basically mark it as 1. The second one is also positive here, third one is negative here, fourth one is negative here, fifth one is here, sixth one is here, and so on and so forth. So, if I find out the distribution of these errors and plot it, so let me plot using another different color. This will be a normal distribution with a 0 mean along the x axis, and the variance which would be there is basically sigma square epsilon I, which you have already noted down. Number 1. Number 2 is that why are we trying the line, blue one line which we fitted, you would basically have some query that why did we use that and why did we place it here, not above, not below something. So, I have drawn it arbitrarily, but there is a reason for that. What we are trying to do is that we are trying to basically minimize the sum of the squares. Now listen to this statement very carefully. If I am saying that I am trying to minimize the sum of the squares or finding out the average of the sum of the squares and trying to minimize that, technically it means that you are trying to do something to do with the variance, because variance basically means the sum of the difference of the squares. So, variance technically we take as expected value of x minus mu whole square. So, what is x? X are the actual values. What is mu? Mu is the average value. So, this actual value minus average value is the error, square it. This actual value minus the mean value is the error, square it. So, this is the error for the third case, square it. This is the error for the fourth case, square it. This is the error for the fifth case, sixth case, seventh case, eighth case. So, what I am doing is that finding out the errors, summing them up and trying to basically minimize, and minimize obviously you will put it to 0 because you want to basically minimize the error. Now, question is that you will minimize with respect to what? Now, if you remember, I did mention that when we were discussing about alpha and beta, we said that given x 1 to x n and y 1 to y n, x 1 to x n and y 1 to y n, we want to basically predict that what would be the predicted value or the forecasted value of y in the nth plus 1 period, compare that with y actual at the nth plus 1 period and try to find out that how does this error basically match. So, technically what we are doing, and we also mentioned that the alpha and beta values are unknown. So, in the case if the alpha values and beta values are unknown, in this case you have only one alpha and one beta. Consider for the first case alpha is 0. So, in this case this error which you have written down, the square values, that is actually sum of y I minus y I hat. Hat is basically the predicted values, square it, and you divide by n because there are m number of readings, this is true. So, this is basically delta of the, so this is the error. So, I will put it as delta. Now, what we do is that square this distance, square this distance, square this distance, square this distance for all of them, add them up and differentiate. Now, this is what you are doing for the differentiation. So, I will remove some portion here. So, basically I will have the error which is basically sum of epsilon 1 plus epsilon n whole square. I will basically differentiate with respect to beta if there is only beta and put it to 0. Now, you will say that from where does the beta come? Now, remember the y hat value is actually, considering there is no alpha, would be beta hat, actually we want to find out, multiplied by x, that means y I or j whatever would be this. So, when we put it, and obviously here see the error is not there. So, technically the y actual value is equal to beta into x plus epsilon. So, when we put the expected predicted value, error is not there. So, the difference between y minus this is equal to y minus this one whole square is equal to exactly equal to y I whole square. So, differentiate with respect to beta, put is 0 and then basically utilize that beta for the prediction of the nth plus 1 value, nth plus 2 value, so on and so forth. So, in the linear regression system we have y is equal to yj or yi is equal to alpha plus beta xj plus epsilon, and the j is equal to 1 to n number of readings. The question is how do we find out alpha and beta, as I mentioned. Provided we have n number of observation which constitute the sample, we minimize the sum of the square of the error with respect to alpha and beta, and this is the error which I told. So, this is the actual value, this is the predicted value, difference from that square it up. So, I am squaring up and this error is differentiated with respect to alpha or beta or gamma whatever it is. So, this will be with alpha put to 0, this will be with respect to beta is equal to put to 0, solve the equations which you have and your work is done. So, finally, the expected value of y would be equal to the predicted value or the estimated value of alpha, which is alpha hat, plus beta hat which you have already found out, beta hat into expected value of x, because in that case the error is not there because you are predicting. And now, the covariances of, obviously there would be a covariances of x and y. We did mention the covariances of the error with x is not there, but obviously there would be covariances between x and y, and that covariance of x and y plus the expected value of x and into expected value of y would be given by the equation. We will be utilizing it later on accordingly. So, after we have found out the estimators of alpha and beta, we use these values to predict or forecast the subsequent future values of y. That is, we find out small y and compare these small y's with the corresponding values of y, capital Y, which is basically the actual value. So, the hat which we put is basically the small values which are the predicted or the estimated, and the capital values is the actual one, difference between them is the error which you want to minimize, the sum of the squares. Thus, we find out the equation y k is equal to alpha hat plus beta hat into x k, and compare them with the corresponding values of capital Y k for k is equal to n plus 1, L plus 2, n plus 3, so on and so forth. So, say for example, if the prediction is absolutely perfect, then the difference in the actual value and the predicted value for the nth plus 1 reading, for the nth plus 2 reading, nth plus 3 reading, so on and so forth. So, if these errors would be there for the nth plus 1 time. So, this is the error for the nth plus 1 time, there would be an error for the nth plus 2 time. So, you will continue, say for example, you take such 1000 values, consider. So, if you add them up and divide by 1000, this is the expected value. So, we know from the formula the expected value is 0, which basically corroborates, actually if it is 0, it corroborates the fact that the assumptions which you have taken corresponding to the case the expected value of the error is 0 and the variance of the errors is sigma square, can be done as a back calculation to prove that the methodology and the way we are proceeding is right. So, assume alpha is equal to 3 for our case, beta is equal to 2 and the equation is equal to y I is equal to alpha plus beta into x I plus epsilon I. So, I is equal to basically the reading number. Consider there are 5 reading numbers month 1, 2, 3, 4, 5. The actual values of y for that time period 1 to 5 are given as 14, 10, 25, 16, 4 and the corresponding xi's are given in the third column starting from 5 to 1. So, obviously, when you multiply the beta, beta is given as 2, beta multiplied by the xi's gives you the values of 2 into 5 which is 10 till the last values which is equal to 2 into 1 which is 2. Now, here the errors is basically the actual value minus the alpha plus beta into xi. So, if you find out in the first case the value which you have is basically you want to basically find out the error. So, in this case the error would be given by alpha is 3, beta into xi is equal to 10 which is basically 13 and the actual value of y is 14. So, 14 minus 13 is 1. So, here the error comes out as 1. In the second case the actual value of y is 10, 2 into 4 is 8 which is beta into xi plus then the value of alpha is equal to 3. So, in this case the actual value of alpha plus beta into xi is equal to 11. So, 10 minus 11 is minus 1. So, all the values which you have found out for the first, second, third, fourth, fifth reading. So, technically if you remember I said that the sum of the errors in the long run should be 0. So, this is just a hypothetical example where you add up the values of the difference between the y actual value and the predicted value which is the error, they turn out to be 0. And obviously, similarly you can find out the variances of the errors, technically it would be constant and that would basically be a certain sigma square value which you should have beforehand, so that you can basically corroborate the overall calculations which you have done. So, with this I will end this lecture and continue more discussion about the multiple linear regression in the next class. Thank you very much and have a nice day.